We talked about last time acid strength. We finished up on, and remember that it really does depend on the type of acids you're dealing with in terms of what you're looking at. When we're dealing with acids that do not have oxygen involved, then we're going to look really at the bond enthalpy or the bond strength as sort of the overwhelmingly uh, property that determines which one is sort of a stronger acid versus another. In group 7, which does contain most of those guys that do not have oxygen, acid strength does increase as you go down the group, and that's because bond energy decreases as you go down the group. When we're looking at oxyacids, which are acids that contain oxygen, we look at one of two things: either the electronegativity of the central atom, or we look at the oxidation state of the central atom. And in terms of electronegativity, we would look at that when the oxidation state of the central atom is the same. So then we would sort of default to electronegativity. And the one with the higher electronegativity would be the stronger acid, because that's again going to basically allow, as we talked about, sort of that hydrogen to come off that OH bond and a lot easier. And that's going to make it a stronger acid. Alternative to that is if we have sort of the same central atom, which means it obviously would have the same electronegativity, we default to oxidation state. And the higher the oxidation state, the stronger the acid would be, for really the same reason. It's going to allow that hydrogen to come off a lot easier than it would in a lower oxidation state. We also talked about the relationship between Kw, that is equal to Ka times Kb. And we get that by looking at something like this. And this would be our Ka expression. You also, again, can leave the water out and you would have something like this, which would also be a Ka. We also could have a base where it would accept the H plus there, make Ha plus OH minus Kb. Now, as we talked about, sometimes you may be given the wrong K value. You may need a Ka when you are given a Kb and vice versa. You use Kw, which is still that 1 times 10 to the minus 14 value to convert between each of those guys. Now, people always have a problem with when you should use which one, and it's pretty straightforward. And again, this is why it's important to be able to write equations correctly. When you write an equation and you have H plus, or if you have H3O plus on your product side, you should be using a Ka value in that calculation. If you write an equation and you see OH minus over here, you should be using a Kb value. So again, really important to write those equations correctly so that you can see if you're producing H plus or OH minus. And then when you would want to do the sort of calculation that's necessary, you want to make sure you're choosing either the correct Ka or Kb value. We're going to talk about today, which are salts, are typical problems where you are sort of given the wrong K value and you need really the other K value. And again, using that Kw as a way to basically convert between them. It's pretty straightforward. It's the 1 times 10 to minus 14 divided by either the Ka or the Kb will give you the other one also in a table. If you can't find a Ka or Kb value, you can use that to figure out what the value would be. Any questions on that stuff there? So let's then talk about that, and we're going to talk about salts and acid-base property of salts. And when we talk about salts, as you should hopefully know, when you take a acid plus a base, you typically will get two things. You typically will get a salt and water. Now, this salt is really just an ionic compound, which means it's a kind of metal, non-metal situation, positive, negative guy sort of happening. Now, the importance of salts is a couple fold, and also something that we talked about last time as well, which is really important, is the relationship between the acid and its conjugate base, or the base and its conjugate acid. Again, if you have either a strong acid, you will have a conjugate base, which will really be part of the salt. which will be relatively weak. And if you have a weak acid, its partner, which is the conjugate base, will be relatively strong. And the same thing holds true for bases. If you have something that comes from a strong base, it's going to be relatively weak. And if you have something that comes from a weak base, it will be relatively strong. So what that means is when we do have that situation where we have either a strong conjugate acid or base, conjugate base, and remember that when we're using the word here strong, it's nowhere near as strong as a strong acid or base. It's just strong in the sense of relationship. What that means is it will be able to continue to react with water. And the process of it reacting with water will either affect the pH, make it more acidic, or make it more basic based on the reaction that can happen. So when we say sort of its conjugate partner is strong, that's really what we mean is it has the ability to continue to react with water in a process known as hydrolysis because water is involved. So it has the process of reacting with water. The result of the salt reacting with the water is it will either produce some H plus or OH minus, and that will again affect the pH. So let's talk about some different types of salts. First off, there are neutral salts, and pretty much neutral salts contain an alkali metal, an alkaline earth metal, and if you remember, that's group 1 and 2 on the periodic table. That is what we talk about in terms of where our strong bases really come from. So if you want to think about it that way, you can, or you could just think about it as group 1 and group 2 on the periodic table. These guys are what are referred to as being neutral salts. So if we have a salt like sodium chloride, and if we take that salt, which is sodium chloride, and we had to think about the acid and base combination that made it, what acid and base combination most likely made sodium chloride? Maybe a little hydrochloric acid, yeah, and a little sodium hydroxide, a little double displacement reaction, right? Water and sodium chloride. Hydrochloric acid is a strong acid, which means when we look at the sodium chloride here, its partner there is Cl minus, and it's going to be relatively weak, which means it will not continue to react with water. Really, the sodium comes from something like sodium hydroxide, which is also a strong base, which means it's going to be weak as well, and it will not react with water. So the process here means that essentially we would expect when we do have a neutral salt involved, that the pH would be 7, neutral. Because neither one of those parts of the salt will continue to react with water. So we will end up with a neutral solution. Now, if we take something like sodium acetate is a salt that will break apart into a sodium ion floating around and an acetate ion. Now, when we think about sort of where this salt probably originated from, what acid would most likely sodium acetate come from? Yep, acetic acid and a little sodium hydroxide, perhaps. Yeah. Again, a little double displacement type of situation happening in this situation as we got a negative, positive, positive, negative in this case. And when we look at really the two components of this salt, because it's a strong electrolyte, it's going to basically be floating around in that solution. And it's going to be floating around that solution with water as probably a result of the acetic acid and the sodium hydroxide reacting. We already know from above that sodium is not going to do much in terms of hydrolysis because it is a neutral salt. It comes from really a strong base. But when we think about acetate here, acetic acid is a weak acid, right? Which means this is the conjugate base, and it is going to be relatively strong. Again, sort of that opposite relationship. So in this particular case, because the acetate part of the salt will be relatively strong, it will then react with water. And when it does so, you're going to get a second reaction that's going to occur, which is our acetate plus our water in this case. Now, if you're not sure what's going to happen in this particular case, we know that acetate comes from a weak acid, which means it's going to act as a base when it reacts with water. And the definition of a base is somebody that will accept an H plus, right? So we know it's going to basically act as a base in this case. The result of that is you will actually form pretty much where it came from, which is always the case. So if you're not sure what you get on the other side, it always is where it came from in terms of like the acid in this case. And in that case, when water does lose its H plus, we will produce hydroxide. And if you had to take a guess, this solution should be basic because we're now producing free OH minus in this solution. So this solution would be basic without even doing a calculation because we are now going to produce that free hydroxide ions that are floating around that solution. Any questions on that there? Now, if I were to calculate the pH of this solution, I would need to do an ice table in this case. And a couple of things here. We would do our normal X's and solve for X. In this case, though, when I do solve for X, X is going to equal the hydroxide concentration, which means I could get the POH and then I could get the pH. Also really important when I do my ice table here to figure out my pH, I should use a Ka, Kb, Kc. What should I use here? I would use a Kb since I see hydroxide there, which again is why it's really important to know how to write these equations correctly so that you choose the right thing. So these are really important things here. If you were doing this problem, they most likely would give you the Ka value for acetic acid. So this would be a situation where you would need to use that Kw equals the Ka times the Kb value so that you could kind of flip it to the right K value that you need. And then you could obviously solve the problem. So those are two really common mistakes that people make when they do these type of problems. They use the wrong K value and they don't know how to write the equation correctly. People would write this equation and have H3O plus on the other side, which is not correct. So it's really important to know how to do that. It helps with the calculation part. Any questions on that there? So if we have a salt that basically originated from a combination of a weak acid with a strong base, we would expect that part of that salt to go through hydrolysis. The resulting solution would produce more OH minus, and thus it would end up being a basic solution. Any questions on that one? Now, there's also salts that are acidic salts. So, for example, if you have perhaps what you got there, a little NHCl, I think, right? So if you have a little NHCl, NH4Cl, I guess would be a better one. You would have NH4 plus and Cl minus in this case, right? And this would be our salt and our two parts of the salt here. And again, if you had to sort of venture a guess here as to where that salt came from in terms of the acid and base, I'm sure you're going to tell me it is hydrochloric acid, which does seem logical. And a little ammonia, right? Our weak base there, right? So we have a weak base and a strong acid. That is going to produce our salt. Obviously, in this particular case, we want to see if any part of this will go through hydrolysis. We already know, hopefully, that Cl minus comes from HCl. Those two are related to each other. And again, because the HCl is a strong acid, the Cl minus will be a relatively weak conjugate base and will not go through hydrolysis. So that leaves our friend here, ammonium, which comes from a weak base. And that means that that ammonium should go through hydrolysis as it's going to be relatively strong conjugate acid. So much like with the case of acetate here, our ammonium will continue to react with the water that's in that solution. And what's going to happen is we will get our NH4 plus will react with some water. And once again, if you're not sure what's going to go on with it, it comes from a weak base, which means it's going to act as an acid when it's dealing with water, which means an acid will donate an H plus. So this guy is going to send an H plus over to our water. The result of that is, not surprisingly, as I mentioned before, you will actually get where it came from. So you'll get the NH3 that will be made, and you will produce, in this case, H3O plus. Without doing any calculation, we should expect the solution to be acidic, right? As we are producing H3O plus in this case because of it. If we wanted to, again, calculate the pH, we would do an ice table, and the Ka value I need would be the Ka value, which I said there in that sentence. So we would need the Ka value in this case because we are producing H3O plus. I would say, much like the acetate example I mentioned a second ago, most likely if you were doing this problem, you would be given the Kb value for NH3. So once again, this is where we would use that Ka times Kb equals Kw to switch it over to the correct Ka value. The difference, though, in this case, when you do solve the ice table, that will equal the H plus concentration, which means you could go right in and essentially get your pH of that solution. So there's three types of salts that we come across in acid and bases. One salt that basically comes from a strong acid or a strong base will not go through hydrolysis because it's relatively weak. If we have a salt that basically originated from a weak acid, it will go through hydrolysis and produce hydroxide and be basic. And if we have a salt that basically originated from a weak base, it will go through hydrolysis and produce H3O plus. Any questions on that there? Now, there is actually another way as well that we can produce an acidic solution, and this is with metals. So hydrated metals, for example, that have a large positive charge, like aluminum, chromium, beryllium, a lot of the transition metals as well, will also behave like an acidic salt. Essentially, what's going to happen in this case is we have basically aluminum, and we basically have 6 waters that's surrounding the aluminum. So I'm not going to draw all the waters out. I'll just write them as H2O. And on the 6th one, I will draw it out like this. So on that 6th one there, we do have our OH on each side there. And what happens in this particular case is, this is what's known as a complex ion, by the way, the aluminum part. Another water just traveling around will actually pop off, basically, one of those hydrogens off of one of the waters. The resulting of that is it will form H3O plus from this guy by accepting the H plus. And that is what we see here. What we are left with in terms of our complex ion is 1 water that hasn't been touched, 2 waters that hasn't been touched, 3 waters, 4 waters, and 5 waters that has not been touched, which is why it still has that number of waters intact. And what we took off of one of the waters was an H, which leaves us a OH, which is where that comes from, yeah. And the sign also changes because that's OH minus. Aluminum is +3, so +3 and -1 ends up with a +2 overall charge. But ultimately here, in terms of the hydrolysis part, certain metals that have a high positive charge can act as basically an acidic salt that will produce some more H plus in that solution and affect the pH. Any questions on that there? All right, so why don't you try this? What is the pH of a 0.45 molar potassium chloride solution? So let's take a look at this and see what we got going on. First off, this is a salt, which is really just an ionic compound. And remember, an ionic compound pretty much is a strong electrolyte, which means in that solution, You got some potassium ions floating around. You got some chloride ions basically floating around in that beaker. Well, will K plus go through hydrolysis? It will not. It is part of group 1 and most likely came from the base known as KOH, which is a strong base, so that's not going to do much. Cl minus also most likely came from HCl, which is a strong acid, which means it is not going to go through hydrolysis. That means that this pH is a pH of 7 and should be a neutral salt in this case, as neither of the salts part there will go through hydrolysis. Any questions on that? All right, so let's do one where you might need to do a calculation, which I think you do. So why don't you give it a go, a little ice table action perhaps. Consider the following. You have a 0.3 molar solution of sodium fluoride. The Ka of HF is 7.2 times 10 to the minus 4. What is the pH? I feel like there's the question. There it is. All right, so take a few moments there, calculate it up. Again, kind of an ice table situation. Let's take a look, see how you're doing. So we have a salt here. Again, I know it's a salt because metal, non-metal, it's an ionic compound. That means that in solution, that salt's going to break apart into two ions, a sodium ion and a fluoride ion in this case. So your goal is to really think about, will either part of the salt go through hydrolysis, will continue to react with water. We know from our conversation that sodium is group 1, which means it's a neutral salt, so it's not going to react. How about fluoride? Will it react? Well, fluoride most likely came from who? Things we don't want to overlook in the problem. I see HF, right? That kind of looks like fluoride. And it has a Ka value, which means HF should be a strong or weak acid. Should be a weak acid, which means F minus would be its conjugate base and be relatively strong and will go through hydrolysis. So there's a lot of nice, important information given to you in the problem that sometimes people just sort of overlook. We will expect the fluoride here to go through hydrolysis because it comes from that weak acid. So the reaction that we should have is the fluoride ion will react with water because water is pretty much the hydrolysis part of it. Now, again, if you're not sure how it's going to react, we do know it comes from this weak acid, which once again means it's going to act as a conjugate base, which means it's going to act as a base when it reacts with water, and it's going to accept the H plus. Clearly, it does not have an H to give, so logic also tells us there's no way it could give an H plus, so it's only could accept an H plus in this particular case. When it does so, people always struggle with, what do I put on the other side? Also why it's good to look at the problem, because frankly, it always makes where it came from, which means there is half of the other side for you, which is HF. And when water loses the H plus, it will produce hydroxide in this case. Any questions on how to get to that equation there? Without doing the calculation, this should be acidic, basic, or neutral solution. It should be basic, as we are producing hydroxide in this case. So now we're ready to do our ice table here. We will use 0.3 molar, which it is a 1-to-1 relationship between those two. So it's the same concentration for F minus. The rest of the ice table will be like a normal one, zeros. Change will be minus X plus X plus X. That means when we reach equilibrium, 0.3 minus X, X, and X at this point. Any questions on the ice table here? This is going to go into my K expression here, which would be my products divided by my reactants. Once again, we're not going to include water, right, because it's a liquid. This should be a Ka, B, C, D, E, F, G. Should be a Kb. Once again, we see hydroxide here, so we need a Kb. Again, we are given a Ka and not a Kb in this case, so this is a case where we do need to use our Ka times Kb equals our Kw, which is 1 times 10 to the minus 14 in this case. So that means that the Kb, which is what we need, would be 1 times 10 to the minus 14 divided by the Ka value that was given to us, 7.2 times 10 to the minus 4. And if we do that there, going to give us, we'll call it 1.4 times 10 to the minus 11. So now that we have the correct K value that we need to use, the rest of it is pretty straightforward here. We're going to go into our KB expression, which will give us x squared divided by 0.3 minus x equals, once again, our KB value. That is a pretty small value of KB, which means we could assume x is equal to 0. And that's going to give us x squared divided by 0.3 equals 1.4 times 10 to the minus 11. We're going to multiply the 0.3 to the other side and also take the square root of it. So we're going to multiply and then square root. So we'll do that times 0.3, a little square root action. And that's going to give us a x value here of 2.04 times 10 to the minus 6. We still need to check it like we've done before. So we're going to take that and divide it by 0.3 and times it by 100%. And I think we're good in this case. I don't even think you're anywhere near even 0.1%. So this estimate here is good. Any questions on that so far? So that means that this X value would be our hydroxide concentration. And that means that we could calculate the pOH in this case. The pOH will equal minus the log of 2.04 times 10 to the minus 6. Minus 6, if I get it right there. So we'll do minus the log of that. And that is a 5.69. Now, if for some reason you thought that this was the pH, would that make sense? It would not make sense because you know it should be basic. So again, this is why it's really important to write the equations and have that understanding of what you should expect in terms of your calculation. So clearly here to get to the pH, I'm just going to squeeze it right there in the middle so it's easier to see. pH would be 14 minus our pOH, which would give us 14 minus 5.69. And that's going to give us an 831 pH, which does make sense, right? Because that is basic and that's what we would expect to happen here. So I can't tell you how important it is to have those understandings, writing these equations correctly. It helps make sure that you're not doing any weird math or thinking wrong about things. You actually have to think about what's going on, yes, so that you get the right answer. Any questions on any of those steps there? Okay, so why don't we try then another one and see, as I scribble on the page apparently. All right, so why don't you try this one here. What is the pH of a 0.75 molar sodium cyanide solution? Okay, so let's take a look. Once again, we have a salt here. So really the first thing you want to try to identify is, where these things come from and will it go through hydrolysis? We have already up to this point seen sodium a number of times. And again, we know that it's not going to go through hydrolysis. So we really don't have to worry about the sodium. The cyanide here, again, if you're not familiar with it, don't overlook some information in the problem. Ka for HCN, that seems like where CN minus would come from. And that Ka means that this is a weak acid, which means that this guy here should go through hydrolysis as it's going to be really its conjugate base. That also will tell you how it's going to react with water. It's going to react as a base, like the Bronsted-Lowry definition of a base, which means it's going to accept the H plus. So again, I can't tell you how many times people just kind of overlook the information in there. It does give you a lot of ways to solve this. So where we want to start with is our reaction. So, and again, logic also tells us that even if you couldn't sort of deduce that, CN minus doesn't have an H to give, so it can only receive in this case, right? So that don't overlook logic as well. So when it does that, once again, if you're not sure, it will always make where it came from, which is also given to you in the problem. So again, you have pretty much the other side of the arrow that you need. It's always going to be where it came from is where you got. Our H2O is going to lose an H plus, which means we are going to be left with OH minus. And just like the previous one, as soon as we see that OH minus, we know that it should be a basic solution. We also know that when we do our calculation, we should use a KB, right? So those again are two things you want to think about as you go through these type of problems. So we can do our ice table here. We're going to use 0.75 molar. Once again, it is a 1-to-1 relationship between sodium cyanide and cyanide, so the same concentration. 0 and 0. Change minus X, plus X, plus X. That means here 0.75 minus X, X, and X. Any questions on the ice table here? As we just talked about, this is going to go into our KB, which will be our HCN, our OH minus, and our CN minus. And we should probably calculate that as well. So our KB will be our KW divided by the Ka value, which was what was given to us here, the Ka value. And if we put that in there, that's going to give us 1 times 10 to the minus 14. Put a 1 in front of that. Divided by 6.2 times 10 to the minus 10. And again, making sure to use our exponent button. That is going to get us, we'll go 1.6 to the minus 5, I believe. So I'm just going to put that right there, 1.6 times 10 to the minus 5. Putting in our equilibrium line will give us x squared 0.75 minus x. Once again, that is a small value of k, so worked on the first one. Why not try on the second one? So once again, I'm going to make the assumption that x is equal to 0. As we've talked about, only the x we're subtracting in this case is going to 0 out. That will give us x squared divided by 0.75 equals our KB value. Once again, we're going to multiply and then square root to the other side, yeah. So we're going to take that times 0.75, a little square root action. Going to get us, if I get my pen there, an x value of 3.478 times 10 to the minus 3. We're going to check it here by dividing by 0.75 and times it by 100. Remember, we're using the 5% rule. And if as long as it's less than 5%, if I don't multiply by 1,000, it will be about 0.5%, which means it is a good, right, assumption in this case. Once again, a reminder that importance of writing this equation correctly, and you are required to write the equations and reactions, by the way. We see that the X value here does equal the hydroxide concentration. So we're going to, I'll do a little rounding maybe. We're going to go into our POH, which will be minus the log of 3.48 times 10 to the minus 3. And that's going to get us a 2.46. Once again, if for some reason you were thinking that's the pH, it should not make sense to you. So we do need to take our pH, will be 14 minus our POH. Gives us 14 minus 2.46. And that's an 1154, which definitely is basic, yeah, and does make sense in this case. Question on any of those things. Hardest part for most people writing the equation, remembering to use the correct K value. So again, don't overcomplicate it. If you get the equation correctly, which you should hopefully be able to do, you see the H plus or H3O plus on the product side, Ka, COH minus on the product side, Kb. Yeah, and that's always how you determine should you use Ka or Kb is by what you have on the product side, either free hydroxide or free H3O plus. Any questions on that there? Now, clearly, we didn't do an example there of an acidic one, but it works the same way. You just got to swap your Kb for your Ka. When you solve for X, you'll just have the H3O plus, and it'll be your pH at that point. Any questions on salts? How to calculate the pH of salts? Here's a much prettier picture of the aluminum working as an acidic salt, but again, these are all the water molecules attached to the aluminum in the middle. And again, just another water molecule is going to pull off a hydrogen and create that H3O plus. Now, in all of our examples that we've done so far, this salt, only one part of the salt will go through hydrolysis. It is possible that you could have a salt that actually both parts will go through hydrolysis. So for example, if you had a little ammonium nitrite, that is ammonium and nitrite, that comes from NH3, which means that would go through hydrolysis. That comes from nitrous acid, which is a weak acid, and that would also go through hydrolysis. So it is possible to have a salt where both parts go through hydrolysis at the same time. Nobody wants to do that calculation of them together. So typically in that situation, if you do come across a salt where both parts of them can go through hydrolysis, we actually compare the Ka value to the Kb value. So if the Kb value for the anion is larger than the Ka value, we will assume it will be basic, and you would just do the Kb calculation. If you compare it and the Kb value is less than the Ka, or the Ka value is greater than the Kb value, we would assume it will go the acidic route and basically do the Ka calculation. If they're about the same, probably you got a neutral situation sort of developing. So here are some where, again, both of the guys could actually go through some hydrolysis. In that case, we don't do both calculations. We do compare the Ka to the Kb. And again, whichever one's larger is the calculation that we do. And we sort of assume that is how the solution would happen. That also happens for things like this, which is amphoteric. It could go both ways, give an H and accept and donate an H and accept an H. And you would actually compare the Ka value to the Kb value for both of those reactions. And again, whichever one's larger would be which way you would expect it to go. So in case you do come across one, that is how you would approach it, by comparing those values. Also another place where you might need to use the Ka times Kb equals Kw to do that comparison. Any questions on that? These are some oxides. Good talk. And oxides are obviously elements with oxygen. And these are our basic oxides, which pretty much means these are where we find our strong bases come from. A little reaction with water will produce like sodium hydroxide, potassium hydroxide, and so forth. A lot of our acids actually come from nonmetal oxides. So nonmetals with oxygen, like nitric acid, like if you take some water and a little bit of carbon dioxide, you get H3CO3, which is H2CO3. That's even better, which is carbonic acid. And again, that's where a lot of those sort of acids come from. There are some amphoteric oxides, and these guys over here are amphoteric, which means, again, they could go both ways. They could act either as an acid or a base when they react with water. So pretty much on the left-hand side of the periodic table is where we find really all of our basic oxides, and that's sort of a forerunner to all of our bases being made. And on the right-hand side where our nonmetals are is sort of a forerunner for how we get to our acids, especially our oxyacids being made. Now, we talked about a couple of definitions of an acid and base. We talked about the Arrhenius definition, which is an acid will produce H3O plus or H plus in water. The Bronsted-Lowry definition of an acid is a proton donor. Our friend Lewis felt left out. So when we think about Lewis, we think about what? Lewis structures, and that's all about electrons. So Lewis came about and defined a Lewis acid as a substance that will accept a pair of electrons. While he said a Lewis base is a substance that will donate a pair of electrons. So it's opposite of Bronsted-Lowry in terms of accepting and donating, and it's also about electrons rather than H pluses. We will see Lewis bases and Lewis acids later on in the semester when we talk about transition metals and complex ions. That's all about basically Lewis acid base sort of interaction. So a Lewis acid, once again, is something that will accept a pair of electrons. Typically, things that are able to accept a pair of electrons are things that are thought of as being electron deficient, and things that typically have a positive charge are electron deficient, right? Because that's how they get a positive charge. So those are things that like to accept electrons. Your incomplete octet guy, like boron, that only has 6 electrons, electron deficient, likes to accept electrons. Things that are good Lewis bases are things that have electrons to give, which typically means they are polar and they got some non-bonding electrons, like water's a very good Lewis base. Ammonia, NH3, is also a really good Lewis base. And things that have a negative charge, right? In order to get a negative charge, you have to gain electrons, which means you have extra electrons to give. So things that are negatively charged are really good Lewis bases. So if we look at something like this, like hydroxide here, in this case, our OH minus has a pair of electrons to donate to our deficient H plus, and that means that this is going to be my acid and this is going to be my base. NH3, which is a polar molecule, has these non-bonding electrons to donate over to the H plus, which means this is going to be my acid, this will be my base. Surprisingly enough, that is the same result in terms of acid and base that you get with the Bronsted-Lowry definition, right? Bronsted-Lowry definition is this guy's going to donate the H plus over, which means that's the acid and the other guy's the base. This guy's going to donate the H plus over, which means that guy's the acid and the other guy, the NH3 there, is going to be the base. So they do give you the same result in terms of what's an acid and what's a base, except that they do look at something different. Where Lewis acid and bases really sort of shine better than, say, Bronsted-Lowry bases is when you're dealing with something that does not involve H pluses being transferred. So we look at something where there is no H plus, like in this situation here, boron trifluoride and ammonia, there is no H's, but this guy's going to donate its electron pair over, which means he's going to be our base, and that is going to be our acid. So you could apply sort of an acid-base definition to something that does not involve H pluses being donated. And again, that boron is going to be electron deficient in this case. Any questions on that? So we will see Lewis acids and bases pop up in a couple other chapters along the way. And definitely when we get to transition metals, complex ions, it's all about really Lewis acid and base is sort of how they interact with one another in terms of the relationship. Any questions on that there? All right, so last thing we're going to talk about in this chapter is our friend polyprotic acids. Polyprotic acids are acids that have more than one hydrogen to give. Now, by the way, the hydrogens do come off in a stepwise fashion. They do not lose all the hydrogens at once. So, for example, we have something like HCl, that is a monoprotic acid, right? It's got one H to give. H2SO4 is a diprotic acid. It's got 2 hydrogens to give. And something like our friend phosphoric acid is a triprotic acid. It has 3 hydrogens to give. Once again, you could also symbolize these by generic formulas of like HA, H2A, and H3A. Maybe a throwback to 200A when you did the titration experiment. That's sort of what was going on there. Now, if we take something like phosphoric acid, for example, it actually comes off, as I mentioned, in a stepwise fashion. So the very first thing that would happen is the H3PO4 would basically give away 1 H plus, and you would be left with H2PO4 minus. And this has a Ka value, which is sometimes referred to as a Ka1 value. And we have it down below there. Looks like 7.5 times 10 to the minus 3. What will happen next is that guy that's already lost 1 hydrogen will then pretty much pop off the next hydrogen. And you will be left with HPO4 2 minus. And that is the Ka2 value. And that looks something like 6.2 minus 8, I think. Yep, minus 8. So 6.2 times 10 to the minus 8 in this particular case. And lastly, what will happen in this situation is that third guy, I'll write it this way, which I think will be easier to see. This guy here, which has already lost 2 hydrogens, will lose the last hydrogen and make a little phosphate action happening there. The Ka3 value for this guy, whatever it says there, 4.8 to the minus 13, I think. So it is a stepwise fashion where each of them are equilibrium type of reactions that are happening. Is it easier to remove the first hydrogen or the last one? Which one's easier to remove? It is the first one that is much easier to remove. It's neutral. So you pop off that H plus, you now have something that's negatively charged and you're trying to remove something that's positive. Second one gets a lot harder. And the third one gets even harder because now you have a -2 charge and you're trying to rip off something that's positive from that. It gets harder and harder. We see that with our Ka values. First Ka values times 10 to the minus 3, much larger value than the Ka3 value, which is to the minus 13, right? So larger K value means you have more reactants or products. Larger K value means you have more products, yes? And because you would have more products, you would have a lot more H plus that would come off than when you have the much smaller Ka3 value where you would actually have more reactants, not as much H plus coming off. So it does get harder and harder to remove each hydrogen. We see that with the Ka values in this table. First one is larger than the second. Second one is larger than the third Ka value. Same thing here for this guy. Large value, smaller value, and so forth. Large value, smaller value as well. So you will find a table like this that has your Ka1, Ka2, Ka3 value. As we talked about, you will find occasionally here, in most cases, sulfuric acid up there on the table, but really the first H2SO4 is a strong acid, so it doesn't really have a number that's very useful, but that HSO4 minus is definitely a weak acid, which does have a value to it. So how do we solve pH problems for polyprotic acids? Let's go through one here, and we'll use phosphoric acid. We'll come back to this guy in just a second. All right, so we're going to basically find everything, the concentration of everything as this phosphoric acid basically breaks apart. We have our Ka1, our Ka2, and our Ka3 value. Once again, as I wrote on the previous slide, our Ka1 for our first hydrogen that comes off, second and third hydrogen that comes off. And if we, again, maybe just rewrite it here so we can see it. So in this particular problem, we're really looking for a lot of information here. In this case, we're looking for the concentration of this guy at equilibrium. We're also looking for this guy's concentration, that guy's concentration, this one's concentration, and the H plus concentration. So we're kind of looking for everybody, basically. So we're going to start with a 5 molar solution of phosphoric acid, and we're going to start with really the first dissociation, right? It's going to lose that first hydrogen. So let us go through this here together and see. So we got our 5 molar phosphoric acid. And the first thing that's going to happen is we have our H3PO4. Going to lose, as we've been talking about there, that first H plus, and we will end up with H2PO4 minus. This again is going to be our Ka1. That was what, 7.4 times 10 to the minus 3. I tried mega memory. I don't know, does that work right or not? 7.5 was pretty close. 7.5 times 10 to the minus 3. All right, so to figure out what's going on here, we're going to use an ice table. We're going to take our 5 molar. This is going to be 0 and 0. Our change here will be minus x, and plus x. That means at equilibrium, we will have 5 minus x, and x. So pretty standard ice table here. This is going to go into our Ka1 expression, which will be our H plus, our H2PO4 minus, divided by our H3PO4. And that's going to equal our 7.5 times 10 to the minus 3. That's going to give us x squared divided by 5.0 minus x. I'm going to go and try to assume that x is equal to 0 here. Hope for the best. X squared over 5 would equal 7.5 times 10 to the minus 3. Once again, we're going to multiply and then square root. So if we do that, that's going to give us an x value of 0.19, we'll call it 4 molar. We do want to check it, so we're going to divide it by 5 and times it by 100%. And if I am not mistaken, in this case, we're at 3.8%, which means my check is good, which is why I changed it from the original concentration to make sure that did work in this particular case. All right, so we have the x value, and really at the end here of this very first ice table that we did, we have a number of answers we're looking for. We have the concentration of H plus would be 0.194 molar, as that equals x. We also have the concentration here of H2PO4 minus, which also equals x. And we also have the concentration of our phosphoric acid at equilibrium, which does not equal x, but we do need to take 5 minus our x. So 5 minus 0.194, going to get us, we'll call it 4.81 in this case. So right off the very first ice table, we're able to kind of check off a lot of things on our list that we're looking for. Any questions on that so far? So if we come back to our problem here, we just found this guy, we found this guy, and we also found that guy. We're still looking for these two guys as well, which means we do need to now go into our Ka2 reaction, as that is where we find this guy. So we do have to kind of go into that guy next. So we're going to go into the second hydrogen coming off so that we can get that concentration that we're looking for. And so that will be our H2PO4 minus, dropping a hydrogen. And also we will then end up with HPO4 2 minus. This will be our Ka2 value there. And once again, that would be 6.2 times 10 to the minus 8. All right, so we're going to do an ice table here. Do I know this concentration? This concentration should come from where? Yeah, the equilibrium line of our first ice table, right? So at this point, we have that much floating around, right? 0.194, our equilibrium here will then become our initial on our next ice table. So if we pop that in there, 0.194. How about H plus? Do we have H plus floating around at this point? We do, also from our initial ice table, right? So we have the same. So we actually have a number over here, and this guy's going to be 0. So again, we're using sort of our equilibrium line there of our previous ice table to figure out our initial table values. Minus x plus x plus x. That means that when we reach equilibrium, 0.194 minus x. By the way, over here is 0.194 plus x, not minus. Yes, so that is plus, and that is x. This is going to go into our Ka2 expression at this point, which is our H plus, our HPO4 2 minus, and our H2PO4 minus. And that's going to equal 6.2 times 10 to the minus 8. I'm going to put that in there. That's going to give me 0.194 plus x times x divided by 0.194 minus x. Yeah. My assumption worked good on the first one, so I'm going to press my luck here and do it again. I'm going to assume that x is equal to 0. That's going to dramatically reduce this down to 0.194 times x divided by 0.194 equals 6.2 times 10 to the minus 8. I'm going to try it without the calculator. Those are going to go away. And that's going to give me an x value of 6.2 times 10 to the minus 8. We again want to check it by dividing by 0.194 and times in by 100%. And I think we should be good here. 6.2 to the minus 8 divided by 0.194 times 100. I can times it by 1,000, it won't matter. It is nowhere even near 0.1%. So the check is good here, yeah? That means in this case, the concentration here of my HPO4 2 minus is equal to X. So the concentration of HPO4 2 minus will equal 6.2 times 10 to the minus 8 molar, yeah? What happens to my H plus concentration if I take 0.194 and add 6.2 times 10 to the minus 8? What do I end up with? I end up with 0.194. It pretty much doesn't change, right? Same thing over here. If I take 1.194 and subtract the X value, you will pretty much still have 0.194. So those two concentrations still pretty much going to be the same as what we had going into here. Any questions on that there? So if we go back to our question here, we just found this guy's concentration. That's going to leave us phosphate, which the only place we have phosphate is in the third step that's happening here. So we are going to have to kind of go to that third step there so that we could get the phosphate's concentration. So let us do that here. Maybe. And the third step would be our HPO4 2 minus. We'll break apart into H plus and PO4 3 minus, which is what we're looking for, phosphate. This is going to be our Ka3, which is 4.8 times 10 to the minus 13. Now again here initially, we do have a concentration of our HPO4 2 minus. That is going to be from our equilibrium line of the previous table, will now become our initial of this table. So that's going to be 6.2 times 10 to the minus 8. We still have H plus floating around. And as we talked about, its concentration is still 0.194 molar. And we have none of our phosphate at this point. Any questions on that? So once again, these values are coming basically from the equilibrium line of the previous table. Change is going to be minus x plus x plus x. Equilibrium 6.2 times 10 to the minus 8 minus x. 0.194 plus x and x. This is going to go into our Ka3 expression, which is H plus PO4 3 minus divided by HPO4 2 minus, and that equals 4.8 times 10 to the minus 13. Once again, putting our equilibrium line in will give us 0.194 plus x times x divided by 6.2 times 10 to the minus 8 minus x equals 4.8 times 10 to the minus 13. Once again, we've been pretty good on our sort of assumptions, so why not continue that pattern? We're going to assume that x is equal to 0. That is going to reduce this down to 0.194 times x divided by 6.2 times 10 to the minus 8 equals 4.8 times 10 to the minus 13. We're going to multiply this guy, come back and divide that guy, right? So we'll do that. And that is going to get us an x value of 1.5. 1.5 times 10 to the minus 19. Once again, we should check it. We'll divide by the larger number, 0.194, and times it by 100. The check is good here. Again, not even 1%, not even 0.1% really. So in this case, that is going to be our phosphates concentration that we're looking for. So the concentration of phosphate in this guy would be 1.5 times 10 to the minus 19 molar. Yeah. Once again, what happens with our H plus in this case? If I put that number back into the H plus, we still have 0.194. It basically doesn't change. And our HPO4 2 minus also pretty much doesn't change either. Question on that. So when you're dealing with polyprotic acids, as we see in this example, if we go back to the first one, the amount of H plus that came off with the first hydrogen is 0.194, right? When we try to rip off the second hydrogen, essentially we only got about 6.2 times 10 to the minus 8 more of it to come off, right? Not very much. And when we try to rip off that third hydrogen, 1.5 times 10 to the minus 19, barely any of it coming off. The majority of all the hydrogen that came off in the first step, which is the easiest step to do. Now, because of that, we could use that to calculate our pH. Our pH in this case would be minus the log of 0.194, which was the last thing it was looking for. And we got a pH of 0.71, which is definitely acidic in this particular case. And I would say if you come across a problem that involves a polyprotic acid and the only thing that you need to calculate is pH, I would just do the first step, and that will pretty much give you the H plus concentration that you need to calculate the pH. In this problem, though, because we wanted the concentration of everybody, we had to kind of go through each of the steps to get there. But again, if you're pretty much just looking at pH, all you have to do is pretty much do that first step, and you will most likely get the correct answer. Question on polyprotic acids. And that's pretty much what that says. Pretty much the first H plus is going to be the one that's going to probably determine the most H plus is going to come off. Any questions on that? All right, so that should be